Hi, everybody. Today we're going to talk about significant figures. Significant figures are a very important topic in science because they help us prevent giving information, data that is overly precise. When we measure with a device, there is a certain limitation to the precision to which that device can actually measure. And when we do mathematical operations, we can find that these mathematical operations can add a certain number of decimal spots to those measurements. So, for example, if I have a length and a width and I need to find an area, I could end up with extra decimal spots. I'll show you an example of this in a minute. Dating way back in time, we use significant figures because when we were doing hand calculations, we had to be very, very cautious that we didn't keep adding decimals from one calculation to the next to the next. Now with computers and with calculators, we are making many more calculations at one time. We're dealing with orders of operations in the computer system or on the calculator, and so the rules have changed slightly. Ultimately, the objective, the purpose of significant figures is to prevent us from giving an answer to a calculation that we could not actually measure with the devices we have, to give too much significance to the extra decimal spots. Let me go through how this works. As I mentioned to you, if I have a rectangle and I were to measure this, and let's say I measure this side as 3.45 meters, and I measure the other side of this as 2.73 meters, when I multiply these together to find the area, length times width, I end up with a value of 9.4185 meters squared, which makes some sense because when we multiply it together, this has two decimal spots and this has two decimal spots, so my answer has 4 decimal spots. I was never able to measure out this far. And so what that means is that if I write that down as the actual area of this rectangle, I am saying that I have been able to measure this to a greater significance than is physically possible with my devices. So how should we handle this? Well, depending on whether we're multiplying or we are adding, we use different sets of rules. Let's start off with the basic addition rules. Let's say that I have 3.51 plus 2.3. When I add these together, I end up with 5.81. My answer cannot have any more decimals than the number with the least number of decimals when adding. So 3.51 has 2 decimal spots, 1, 2, and 2.3 has 1 decimal spot. 2.3 has just the 3. And so my answer can only have, it has to have the least. We always want to go to the one that creates the greatest amount of error. We don't want to go too specific. And so on my answer here, my correct answer in reporting this would be 5.8. The same thing happens with subtraction. If I have 7.83 minus 2.5, I end up with 5.33, 5 and 33 hundredths. Again, 2 decimal spots, 1 decimal spot. My answer can only have 1 decimal spot. So the 3 is irrelevant. So this is how we deal with the addition and subtraction rules. Now, the second set of rules that we deal with multiplication and division. The multiplication and division rules require us to look at leading and trailing zeros. A leading zero would be something like this, 53 10,000ths, and the leading zeros are these zeros. A trailing zero would be a zero that I add on to the end of this. So some of those numbers are what we would call significant and others are not. There are many ways to do this, and one of the ways that I see commonly done is the students memorize a set of rules. There is nothing wrong with that method. The method that I am going to recommend you use, and it is just that, a recommendation. You can use whichever method works for you. I care that you get the right answers. How you do that is, again, up to you. But what I recommend is using a method called the Atlantic and Pacific rule. That's why we have a picture of the oceans up here. This is the Atlantic Ocean. This is the Pacific Ocean. The Atlantic Ocean starts with an A, and absent starts with an A. The Pacific Ocean starts with a P, and present also starts with a P. Absent and present. These terms we use because we look and see if there is a decimal point present or absent. So in the number 5,300, there is no written decimal point. We would say in this case, the decimal point is absent. In the number that I originally wrote up here, there was a decimal point present. So we'd use the Pacific rule. The way the Atlantic and Pacific rule goes is that we start off by looking to see if we are present or absent with the decimal spot. In the number 5,300, we are absent. So we start on the Atlantic side of the number. This is the Atlantic side. This is the Atlantic side. We then move across the number until we reach the first non-zero number. We move just like we're moving across the country. We move till we get to the first non-zero number. That number is the 3. Every number moving across the country to the left from the A side towards the P side is going to be significant. So in this case, there are 2 significant figures. In the case, 2 significant figures. In the case of the 53 10,000ths, as it's written on the screen right now, there is a decimal point present. We will move across the country towards the A side. P present, move towards the A side. And so as I move across, you start counting when you get to the first non-zero number. So there, I start at the decimal. The first zero is a 0, so it doesn't count. The next 0 is a 0, it doesn't count. Then I get to the first non-zero number. Every number after that, moving rightward, is significant. So 1, 2, 3, 4. All 4 numbers are significant. So this has 4 significant figures. That's how the Atlantic and Pacific rule works. Let's see another example of that. So let's say that I have the number, as I scroll down here, let's say that I have the number 0.031020. So that number would have how many significant figures? Decimal point is present. So we are starting on the P side, moving rightward. We start counting with the first non-zero number. So we have a 0 number, that doesn't count. We have a 0, that doesn't count. 1, 2, and then we keep counting, even though it's a 0, 3, 4, 5. This has 5 significant figures. Here's another one. 5,100,300. So 5,100,300. So we see no decimal point. So the decimal point here is absent. We then move across the country leftward. We start counting with the first non-zero number. That's a 0. It doesn't count. That's a 0. It doesn't count. We have a 3. That's the first non-zero. That's the first non-zero number. That non-zero number would then, every number after it becomes significant. 1, 2, 3, 4, 5. All those numbers from the 3 all the way to the 5 in the 5 million become significant. This has 1, 2, 3, 4, 5 significant figures. So the answer there is also 5 sig figs. Okay, so the next step is to do multiplication with numbers, and we will have to use the significant figure rules for this. When we're adding and subtracting, we use the decimal rules. When we're multiplying or dividing, we use the significant figure rules. So if I have the number 5.13 times 3.2, I end up with a value of 16.416. Now, the 5.13 has 3 significant figures. There are no zeros, so every number is significant. The 3.2 has 2 significant figures. My final answer has to have the same number of significant figures as the factor that gave it the least number of significant figures. So the least would be 2. So my final answer can only have 2 significant figures. When I look at the number 16 and 416 thousandths, it has 5 significant figures. To get 4, you would remove the 6. To get 3, you would remove the 1. To get to 2, you have to go all the way back to just 16. 1, 2. 1, 2, meaning 1 and the 6. So with proper rounding rules, the 4 rounds the 6 down to a 6, and so we're left with 16 as our answer for this particular problem. If I did division, I would have, for example, 7 and 35 hundredths, 7.35. Divide that by 3.125, and I end up with, when I plug into my calculator, 2.352. That had the 7 and 7.35, that has 3 significant figures. The 3.125 has 4 significant figures, and our final answer has 4 significant figures. Our final answer can only have 3, so I have to drop the 2, and I end up with 2.35 as our final answer. So that's how you do multiplication and division. Now, this concept gets hard when you mix. Let's say we are using an equation for the position of an object when we have an object that is moving and it is accelerating at the same time. This equation looks something like this. X is equal to v initial times t plus 1/2 the acceleration times the time squared. That's a equation that you use in physics a lot, but there are equations like this in other mathematical and scientific areas as well. You have to do in this problem order of operations, you have multiplication and addition, and you have squaring. How do you handle this? Well, the way this was handled in 1950 and the way we handle this today is much different because of the advent of a calculator. In a normal science class that is doing this type of a problem, you will plug the numbers into the calculator and get an answer out. The way the significant figure rules were originally thought of is you would do the velocity times time, the first term, get an answer. You would do the 1/2 AT squared, the second term, get an answer. Do the significant figure rules on both of those answers, then combine them together to get your final answer. That is inefficient, and it isn't the way that computers and calculators do math. You would have to slow things down to a level that is unacceptable. And so what we do is we use a combination rule. I'm going to show you what that looks like. Okay, so let's say that we have 50, x equals 50 times, let's say 50.0 times 2.15 plus 1/2 times negative 42.3 times 2.15. Now, these were all measurements of 2.150. There is a zero there. These are all measurements that were made with a stopwatch or a ruler, and the number of decimal spots represents the precision that the instruments can measure. So a stopwatch might be only able to read to the 10th or 100th or 1,000th of a second. A meter stick can only generally read to the millimeter with graduation, and then one guess beyond that. So if you're reporting your answers in meters, you could report it out to the fourth decimal spot, but that fourth decimal spot is a guess. So when I take these numbers and multiply and add them together using proper orders of operations in a calculator, I end up with 9.734125. Now, again, when we did this in the 1950s, we would have ended up with an answer for the first term, and we would have done sig figs. We would have answered up with got an answer for the second term and did sig figs. Then we would add them together and use the decimal rule. But that's not how we plug stuff into computers and calculators today. So we just take this number and plug it in, and the order of operations is done for us. And we end up with this massive number on our calculator. So which rule do we use here? Do we use the rule that requires us to use decimal spots? Do we use the rule that requires us to use sig figs? Does it matter? Let's analyze this both ways. So if we take a look at decimal spots, what we would find is that the 50, the first number there has one decimal spot. The second number, the first number has one decimal spot. The second one has three decimal spots. Then we have one decimal spot, and then we have three. So our answer could have one decimal spot. So in that case, the answer would be, in terms of decimals, 9.7. Now, if we analyze, so that's if you choose the decimal option. If we choose the sig fig option, significant figure option, then we take a look and we see that the first number has 3 sig figs, the next number has 4 sig figs, then 3 sig figs, then 4 sig figs. That trailing zero is significant using the Pacific rule. The two starts are counting, 2, 1, 5, and then that's 0 because we're moving across the country to the right. That's the case with the 50 and the 50 as well, with the 3 sig figs. Those two trailing zeros are also significant. And so in terms of significant figures, we are going to go with the 3 sig fig option. 3 is less than 4. And so in that case, we would get the number 9.73. Our initial intuition is to say, yay, I have more specificity with the 9.73. But remember, the purpose of significant figures is to underestimate our significance, not overestimate it. And so we would choose, in this case, to go with the 9.7 option because that is the least precise measurement. Now, these same numbers give us a different result entirely when we change one sign. Let me change in this problem, let me change the 42.3 from negative to positive. When you plug that into your calculator, and that is now positive, then you would get, if you actually plug that into your calculator under this method, you would get 205.265. Now, same rules apply. 1 decimal, 3 sig figs. You could have the 1 decimal method, you could have the 3 sig figs method. So in terms of decimals, you would have 205.2, and in terms of significant figures, you would only have 205. 205. So which one of these do you choose, the decimal method or the sig fig method? You might have guessed it correctly. You choose the sig fig method. So the same numbers depend on which answer is going to give us the least significant answer, the answer with the least specificity. And so looking at that, we end up with two answers. Every time you do multiple calculations, multiple operations, I should say, you want to take a look at it and say, okay, which one is going to give me the correct number of significant figures? There are some problems that you can try online. If you have any questions, don't hesitate to ask me. I look forward to discussing this with you if you have any concerns. Thank you.